Welcome to the microwave communication course. Today we start here a new topic, the magnetron. The magnetron that is useful for the generation of a microwave signal frequency or a microwave signal. So this magnetron is to be called as a cross-filled tube. Okay, this one is nothing but a one cross-filled tube. So in a cross-filled tube means what? We have the electric field component and a magnetic field component. Both are perpendicular to each other. Okay, so that's why this tube is called as a cross-filled tube. And we have seen earlier that a klystron and traveling wave tube, traveling wave tube amplifier, that devices belongs to the linear tube. So in which your electric field and magnetic field is in a parallel, or we can say that in a axial position. So here we will learn here the magnetron, and in this magnetron we supposed to learn about that how your electrons are bent by the magnetic field. Okay, so that we are learning. Now this magnetron is used generally as an oscillator in most of the circuit, in the radar, okay, everywhere there where we have a radar component, or mostly even if in our oven that magnetron is there. So now we need to learn first principle how this magnetron is working. Okay, so now for that purpose we should know first. So basic principle of a tube, it has some cathode, and that cathode emits the electron there. And then around this particular cathode, this one is about the anode here. This one we supposed to say that a anode, and this one we supposed to say that a cathode. Now in general principle, if you see that a cathode emits the electron, and the velocity of the electron is depending upon that how much is the DC voltage applied to the cathode. So electrons are interacted in this given region, and then electrons try to move from this cathode to the anode here. Okay, that is about the motion of the electrons from the cathode to the anode. Since the anode is about a positive supply and cathode is about a negative supply, so natural process is about what? Electrons will attract it toward the anode, or electrons have some velocity, so that's why electrons are moving in the interaction region. This is nothing but interaction space or a region between the cathode and anode, and then electron get some, they have some velocity, they will move in this particular space, and then they will reach to the anode. So now anode is about a positive, so means electrons are terminated. Now this one is about the motion of electrons here. Okay, if you consider here the motion of electrons is from what? A cathode to the anode here. Okay, that is, this one is about the motion of the electron, that is from the cathode to anode here. Now since this one is about a positive and this one is about a negative, now so if you consider that the capacitor there, so in that case, if it is a positive plate and a negative plate here, so in that case, it will emanate from the positive and terminate at the negative. So similar here. So we have the anode here. That anode is about a positive one and a negative is about a cathode. So that's why we say that a field emanates from what? From this anode to the cathode. Now this is about your electric field. And the direction of the electron is from the cathode to the anode. Means here, so electrons direction, electron motion, okay, from the cathode to the anode, and the field is opposing here. Okay, field is opposite to the motion of the electron. Okay, so means electrons are moving from the cathode to anode, and field is moving from the electric field from the anode to the cathode. So that is about the electric field. So that's why a force exerted by an electric field on an electron, that is proportional to the strength of the field. So we have seen earlier that F is equal to volt minus E into E here. Okay, F is equal to minus E into E. That is about the force exerted by an electric field. Okay, by an electric field on an electron here, because electrons are coming out from this cathode and it will be passed toward this anode here. And this is about electron passing in this given interaction region there. So that is about a tendency of electrons move from the negative and attracted toward the a positive potential. That is about the anode here. But the field emanates from the positive and terminates at the negative. That is about it. So here the force of exertion, okay, force exerted by an electric field on the electron there. Now this is about a in general. Now if supposed to be, we consider that along with that this is a field, electric field. Now this one is about a E here. We supposed to say that electric field. Now if supposed to be, we say that the electron motion in a magnetic field. Okay, if the electron is moving in a magnetic field, so what happens? Then a force exerted on an electron in a magnetic field is that what? What is the value? That is about F is equal to, we have seen earlier, that is about your charge, and we say that V cross B. Okay, that we have seen earlier. That is about the force exerted by the magnetic field on the electron here. So here the V is the velocity of the electron and B is nothing but a magnetic field. Now this one is nothing but depending upon that what will be the, okay, here we supposed to say E minus E, okay, electron charge. So what will be the magnetic field present and what will be the force, total force exerted on the electron by this magnetic field is, and that is depending upon that velocity of the electron. So generally that, consider that we supposed to say that electrons moving from this to this. Now here it is opposite. So what will be the force? We say that magnetron is about a cross field tube. So the force exerted on this one, it is about a perpendicular in nature. So this one, it is about a perpendicular. So we have the field. This one is about the electric field. So we have the magnetic field here. Okay, this one is about a magnetic field. So that's why this tube is supposed to be called as a cross field tube. And this one is supposed to be a board now. So your magnetic field will come out from the board or it will go inside the board here. Okay, it is go inside the board or it will be come out from the board here. That is about the magnetic field. So your electric field and magnetic field, if you consider here, so both are perpendicular to each other. So that's why that magnetron is supposed to be called as a cross field tube. Now, because of a magnetic field, so electron, it will not move directly toward the anode. Based on the field, magnetic field present, so electron will bend their path. So what is the role of a magnetic field? So role is about what? So it will force the electron, uh, for the direction of the electron. Okay. So what happen here? The magnetic field will will whatever the force apply on the electron. So due to that force, the electron will bend their path. So instead of moving directly here, generally we say that for a given particular, so this is about a cathode here. So here in there is a field now. So instead of going directly straight forward here, so electron will bend their path and they will reach toward the cathode. Okay, so they will reach toward the cathode. Even if we increase a more field, so then they will move early toward the cathode. Okay, means it will emit from the cathode and it will return back to the cathode. Now this is about the interaction region. So this one happen. Okay, so now it will try to reach toward the anode, but due to the magnetic field, it will come nearer to the anode, but due to the magnetic field, it will bend their path. So it will be returned back. It will be returned back. But if the magnetic field is too large, so in that case, that electron will move, or they will bend their path as early here, and they will reach toward the cathode. So this one is depending upon that what will be the magnetic field strength we are applying. Okay, what will be the magnetic field strength we are applying? Now, again, this anode has some particular current. Are we supposed to say that this anode is nothing but a plate now? So we supposed to say that a plate current now. Okay, so because we say that we have the a plate from it emanates from the positive and terminates at the negative. So that's why we supposed to consider that anode current here, or that plate is supposed to be plate current here, and some current is there. Okay, so this one is about a current because we have the electrons interacted in this region. Okay, if there is no field, so it will terminate at the anode. Okay, that it is depending upon that how much is the anode current. If the anode current is small, okay, so then what happen? Because of that motion of the electron, so it will increase the anode current here. Okay, it will increase the anode current because electrons emits and terminate at this particular place, at this particular plate, and because of that electron give up their energy, so that's why current at the anode will be increased. Now we supposed to say that if that electron interacted in a magnetic field region, so then they will bend their path. Okay, then electron, that is about the path of that electron, will take a bend, and that bend we supposed to say that is about a sharp bend at this particular anode plate, and due to that, that plate current will be reduced here. That is about a, because electrons are not interacted here, they will not terminate at the anode, so that's why the plate current will be reduced here. Okay, so now we consider that here. So how your a magnetic field and this particular plate current. Okay, this one is about a, we supposed to consider that a plate current. Okay, and this one is about we say a magnetic field strength. Okay, now what happened here? So generally the, when we increase the magnetic field, okay, so plate current increases. Okay, initially we have the highest plate current here, and then at some particular critical value of the magnetic field strength, plate current decreases, or it will be a zero there. And that value of the magnetic field strength is called as a critical value of a field strength. Critical value of a field strength. Now, what do you mean by this? So, in general, we say that electrons, okay, in this particular region, there is a interaction region here. The plate current is high. In that case, electron will move toward this anode now. Now, in the critical condition, so electron will move nearer to the anode, but it will come back to the cathode. Okay, so this one is about electron from the cathode, emits from the cathode, but because of this higher magnetic field strength, so it will reach to the a cathode. Even if you increase, okay, even if we increase further this magnetic field strength, okay, so then what happen here? So electron will move from the cathode and reach toward the anode as early as. possible. Okay, so this one. So it will be reach early. So it is depending upon that what will be the critical value of a field strength. If the critical value of field strength, okay, if the magnetic field strength is more than that of critical value of field strength, so electron will move early. Okay, so they will, because force is large, so that's why electron will bend more. Okay, bending of the electron in the interaction region. So that's why the magnetic field strength, if supposed to be increased, then electron, what will happen here in the initial state, magnetic field if we are increasing, then whatever the electron path is there, so that will path will be curve. Okay, instead of a straight one, so it will be a curve path. If we further increasing this magnetic field there, okay, that magnetic field is reached some critical value there. So in that case, the electron just miss this particular plate here. Okay, they will not reach to the plate. Just miss the plate and return to the cathode here. Okay, this return, that electron will return to the a cathode. And the another case, if the field strength, okay, if the field strength again it will be increased, that will be more than this critical value of a field strength. So in that case, what happens? The electron is travel to the cathode. Okay, electron travel from the cathode and it will be travel back again. Okay, to the cathode. So that is about in a small circular path. It is about, this one is about a large circular path, but this one is about a small circular path. Okay. So this way your electron will be moved from the cathode to the anode. So this one is about a principle, basic principle used in the magnetron. So your electron interacted in a electric field region as well as electron interacted in the magnetic field. Now this one we have seen that electron interacted in the magnetic field. So now we talk about the how electrons are interacted again with the both the things. Electron interacted in the electric field as well as the magnetic. So earlier we have seen that here we have the electron, because we have the magnetic field and, sorry, electric field, and this is about the electron path, that it will be a direct here. But the electron, that electric field is opposed to this path of this electron. Okay, it is opposite here. Now in a magnetron, instead of a anode, okay, directly the anode, so some cavities are there. So anode structure in a, what you can say, that in a magnetron, it is just like a cavity one. So there are the various type of a magnetron. We supposed to say that the types are depending upon that what will be the structures we have in the magnetron. So cylindrical magnetron. So in that case, we have the cathode and the cavities interaction pressure will be different here. Now this one, okay, I supposed to draw a circular one now. Okay, this one is a circular one. Okay, so this one we supposed to consider here, and here this one is about the a anode one. So this one is about a cylindrical magnetron. Okay, so now this one is about a cathode here. We have the cathode, and this one is about a anode here, right? So you supposed to be consider that a interaction region is likewise this one. We supposed to consider that this one we have the interaction region. Okay, so this one is about your interaction region. So I supposed to be consider one, and this one is a cavity portion. So we supposed to say that from this to this is nothing but a cavity here. This to this is nothing but the a cavity. So this to this is nothing but the cavity here. Okay, so likewise we supposed to say that This one is about a cavity. Okay, so likewise. So now if I am just going to draw here. So this one is about a cylindrical magnetron. So now this one is about the interaction region here. So electrons are moving from this. Okay, electrons will be moving from the cathode. This one is about cathode, and this one is about your anode here, and this one is about a cathode. Okay, so we have the positive current for the anode and negative for the cathode. So electrons emit from the cathode. It will interact in this cavity there. Okay, but here what happens? So that these cavities are nothing but the irresonant in nature. Okay, these are whatever the cavities we say. So it has a irresonant in nature. So for each and every alternate cavity, it has some a positive uh, we can say alternating cavities are there, but this cavity is supposed to be it has some capacitive and a inductive component. That is nothing but what we can say a tank circuit. So here for this given particular cavity, alternating current is generated for this particular cavity because electrons are interacted to the cavity there. And then because of this, so cavity becomes at one end it will be a positive. Okay. So because of this, I supposed to say that now here we have the interaction region there. So this particular region, if so, it here it will be a positive and this will be a negative now. This will be in this case it will be positive. This will be negative. So now if you draw here because of this positive and negative, so here there will be field. It emanates from the positive and terminate at the negative. This one is about a electric field. It will be from the positive to the negative. Likewise. Okay, so we have the a field. So now if supposed to be I redraw this part. Okay, if I redraw it in a proper way here. So how it look like? Just like I'm just going to redraw again here so that you people are able to clear it properly. This one is about a cathode. Okay, this one is about a cathode here, and I suppose to draw the a cavity. These are nothing but the a cavity now. Okay, now these are nothing but the a cavity. So now for this cavity, this there will be a electric field. So because of this here, okay. So if supposed to be I take a larger one, okay, I'll take larger one now. Now this one is about a cathode here, and this one is about a anode. This one is nothing but the anode now for the magnetron. Now what happened here? There is a RF field. Okay, there is a RF field because alternating cavity becomes a positive interaction region and negative interaction region. Okay, so this one here. So because of this positive and negative, so field emanates from the positive, okay, and terminate at the negative. Field emanates from the positive, terminate at the negative. So this one is nothing but what we can say your RF field. So similarly, field emitted from the positive terminate at the negative. Okay, so now this one is about your R. So field emitted from the positive terminate at the negative. Right. So this one is about what we can say it is about the electric field. This one is called as a electric field. And now the cathode. Cathode emits from this. Okay, sorry, electron emits from the cathode. It will reach to the anode here. Okay, electron emit from the cathode. It will reach to the anode. But here the cavity spacing here. We're supposed to say that sometimes it is a positive and sometimes it is a negative. When the electrons are interacted to the in this particular region space in this interaction region, okay, in this interaction region, what happened here due to the positive and negative, here it will be attracted, means it will be move faster, and here it will be negative now, okay, because of the negative, so it will be slower here. Okay, so likewise we say that a retarded field is your acceleration of the electron and deceleration of the electron is takes place here, so that is nothing but a velocity modulation takes place here. Okay, so what happened here, if you consider that the, for this a given particular magnetron, so alternate cavity alternate cavities have some particular phase difference, and that alternate cavities phase difference, if supposed to be we consider that a phase difference between the adjoining cavity is supposed to be a pi, okay, is supposed to be a pi, then the magnetron is working in the pi mode of a operation, and in this pi mode of a operation, so you will get the highest efficiency and oscillation will be stable here. So if that alternating cavity is not a pi here, okay, so then what happen? So then your operation will not be what you can say that operation of this uh, magnetron will not be a highly efficient one. So that's why we need to consider that there are the various magnetron circuit, okay, very magnetron tubes. So in which what will be the modes of operation of the magnetron? It is depending upon that what will be the phase of this alternating cavities there. So generally we supposed to be consider that the phase will be of a 2 and pi now. Okay, so that is about a 2 and pi. Now in this case, in this alternating cavity here, we supposed to say that it is about a pi mode of a operation now. So generally that how many number of cavities are present there. Okay, so then we supposed to be consider that adjacent mode of the cavities and their operation there. So generally pi mode of operations are used, and that pi mode of operations will use the highest efficient oscillation. Okay, it's a stable operation. And whatever the cavities we are using, so these cavities have the high Q, so that a resonant frequency of the cavities and frequency generated through this magnetron circuit, so it will be a similar now. Generally, we supposed to be consider it is a similar one. Now, what will be the micro frequency? Okay, that is about generation of micro. In whatever we say, that it is about a gigahertz, but that frequency is depending upon that what will be the interaction region we have. That is about a magnetic field exerted on this. So generally here we say that a cathode. This one is about your electric field. So what about the magnetic field? So magnetic field will be a, a perpendicular one. So likewise, we supposed to consider that about a magnetic field here. Okay, we supposed to be consider that we have the generally we supposed to be use a magnetron. So there will be a given for a given interaction region. So there will be a we can say that a magnets to be used. And in this case, we have the magnetron, south pole and north pole. Okay, this is one yes, and this one is the bottom. So here, so we have the magnetic field will be generated in between that a cathode and a anode. Now we talk about that how these electrons will reach toward this anode. So generally, because of that, whatever the magnetic field is there present, magnetic field is present. So electrons will move toward the anode if that magnetic field strength is small here. And if there is a RF field, this was about your, we can say that whatever the RF field is present there, or RF, whatever we can say that a field is present or a field is absent. So in that case, if the field is present, then electron will bend their path. If the field is absent, then electron will, sorry, if the field is absent, then electron will move from the cathode to the anode directly there. Now this one is about a RF field. We are supposed to say here, when electrons are moving from the cathode, okay, it will pass through the, in this particular interaction region, there is a RF field, and that RF field is about supposed to be that it is about at this particular, the direction of this RF field, that this one electric field we say here, and the electron here, interaction region electron here, it's supposed to be opposite here. Okay, and somewhere we say that direction, because electron moving from the cathode, because of that magnetic field, it will bend their path. Okay, electron will bend their path. So that's why the path of that electron, it will be a parallel to the magnet, this RF field here. So means that is about the motion of that electron. Because of this magnetic field, it bend their path, and because of that bending the path, so they will interact it to this RF field. Okay, they will interact it to this RF field, and then when they will interact it to the RF field, they will give up their energy to the RF. And once they give up their energy to the RF field, then sustained oscillation takes place inside the cavity, and then that your magnetron will work as an oscillator. Now we consider that only single electron we supposed to be considered, but here the bunches of the electrons are formed because of the a field here. So generally that electron field, okay, that is about the electron, and there will be a RF field component. This one is about a tangential field component, and this one is about your a magnetic field. And because of that, electron retarded by the field and give their energy to the field now. If the we can say that this one is about a tangential electric, that RF field here. Now, if supposed to be that position of, what will be the position of the electron here? So from this it started now. If it will, it if yeah, that whatever we can say that a RF field is present here, if that whatever the electron is here, if that electron having the energy, okay, whatever we can say that that velocity of the electron, okay, they are interacted in this region here. So because of this RF field, so then they have to give the energy to the RF field. But what happened here? So since this is about a cavity has a alternating polarity, so that's why electrons will be displaced here. Okay, so they will not reach toward the that particular region. Okay, so because of this, what happened here? So electron will move their path in a different direction. So likewise, I suppose to consider that instead of bending here, so it will reach at some particular place. So this one is about the electron bend by the magnetic field, and slowly it will be terminate at the anode plate. Nothing about a single. So there are the more number of electrons. They will move and they will bend here. So at the end, the electrons will terminate at this plate and they will give up their energy to the RF field. So how it will be looks like when we supposed to be consider this about a cathode. So electrons will move like this particular path, more number of electrons, and then it will just looks like that is about a spokes one. Okay, so here there will be a motion of the electron. So this will be looks like a spoke structure here. So here electron will bend their path and it will be moving now. This one. So whatever the because it is just like a that electron has a outward force now. Okay, it will have the outward force because of that a magnetic field there. So this one is about a spokes like structure occur when large number of electrons emitted from the cathode and it will because of whatever the high value of a DC voltage we apply. So that's why that motion of the electron will be straight. But electrons are interacted in this magnetic field region with this RF field, alternate field. Okay, here. And because of that, electron will move faster or electron will move slower here. So path of the electron will be bent by the magnetic field as well as by the electric field here. Okay, so this way. So because they will, if that electrons are interacted in the positive cycle or electrons will be interacted in the negative cycle, so according to that, a electrons will be accelerated or a decelerated. So same thing, there will be a velocity modulation takes place here. Okay, so means because of that velocity modulation here, so then bunches of the electrons are formed likewise here. So these are nothing but the bunches of the electrons are formed and they will reach at this end here. Okay, so that's why. So if you see the overall diagram, so this there will be a group of the electrons and that group of the electrons are creating the spoke shaped space charge. Okay, this one is about a spoke shaped space charge cloud of the electrons there. And there will be a one spoke here because of this for every alternate cavity. Okay, because alternate cavity is about a positive here. Positive here, this one is about a negative. And spoke charges occur means it will terminate at a positive. So next electron motion will terminate at a positive. Next will be positive. So likewise. So this one will be the alternating cavity. This will be positive. This will be negative. This will be positive. This will be positive. This will be negative. Likewise. So here it will be a negative interaction region. This will be a positive one. So this one will be negative. So likewise. So alternately here, this spokes type of this particular space charge, okay, that cloud of that electron will be moving here. And this box is rotating with an angular velocity. And that angular velocity is equivalent to that how many number of poles we are using here. Okay, there we can say that generally we supposed to be consider that a direction it is about a clockwise one. Okay, so likewise we supposed to consider, but this one is about a spokes like that. Okay, this one is about your, we can say that a electron orbit now. So that's all about what we can say that a magnetron here, and here in a magnetron, so we supposed to consider that a RF field that is about electric field as well as a magnetic field there, and in which we supposed to consider that a magnetic flux line are passing through the cavities and that are parallel to the a cathode axis. Now this is about a cathode axis. So magnetic field is a parallel now, and this one is about your electric field line. So here a RF field that will be concentrated at this particular cavities or at the particular slot there in that particular interaction region there are the various types of a what we can say that a magnetron there, and we supposed to consider here the pi mode of operation, and we supposed to consider here the a cavity type magnetron. Okay, so if we supposed to say that a cylinder, that is about a cylindrical one or a cavity one. Okay, so that about what you can say that a various types of a magnetron. And now we talk about that other types of a magnetron. So in other types of a magnetron, so there will be that anode we supposed to be considered here. That is about a different structure. So generally we say that a split anode type, or we can say that a cyclotron frequency magnetron, or we supposed to say that a backward wave oscillator. So likewise, there are the various types of a magnetron, or in here we supposed to see that a traveling wave magnetron, and in which we are just going to learn that that about a coaxial type, or you can say that is a cylindrical type of a magnetron. And if you see the performance characteristics of a magnetron, so performance characteristics of a magnetron, it is depending upon that what will be the anode voltage and what will be the anode current. If we supposed to increase the anode voltage here, okay, if we supposed to increase the anode voltage, then your output power of this magnetron as well as efficiency, okay, both are depending upon that anode voltage and the anode current. So generally we say that a power output by this magnetron, it will be large, and that will be up to a 400 kilowatt or more than the 100 kilowatt. And the operating frequency of the magnetron is about a 500 megahertz to the 2 gigahertz, or somehow some cases we are going to achieve that micro frequency is up to a 10 gigahertz there, and efficiency of the magnetron, it is about the 40 to 70%. And we can use this magnetron mostly in a radar applications there, or we supposed to use the magnetron for the dielectric heating in the industry there, and in which we supposed to use a 500 megahertz to 2 gigahertz of a frequency there. Again, this magnetron can be used in a airborne missile and a satellite and a Doppler system there. So that's all about your magnetron there. So thank you all of you.